Welcome back to the Deep Dive, the show that takes the complex, often opaque world of cloud infrastructure documentation and really distills it into actionable knowledge.
Mm,
If you are operating anything substantial in the modern tech landscape, you're dealing with massive amounts of object storage.
absolutely.
And if you're in the Google ecosystem, that means navigating the, virtually infinite, highly scalable world of Google Cloud Storage or GCS.
And that scalability is magnificent. It really is. But it comes wrapped in a financial complexity that catches far too many teams off guard.
Right.
GCS isn't priced like uh, simple warehouse space.
hmm
It's a multifaceted model where data temperature, data movement,
Okay.
and the operational chattiness of your applications all kind of interact. Most people just look at that tantalizingly low cost per gigabyte of archive storage
Yeah.
and think they've solved their budget problems.
I can see that.
Only to realize later that they've signed up for a whole series of hidden fees that are just actively draining their resources.
That cloud sticker shock phenomenon is so real, especially when, engineers or even financial planners miscalculate how often or how quickly their archived data actually needs to be accessed.
That's it.
The difference between saving $100 a month on storage and spending $1,000 on retrieval fees can be a single overlooked click. So what's our mission for this deep dive? We've got a whole stack of docs here, pricing guides, best practices.
Our mission is to move you, the listener, beyond that simple storage cost figure. We're going to extract the core financial nuggets you need for disciplined, effective cost management.
hmm
We need to clearly define the four distinct ways GCS takes your money, and crucially, show you exactly how the decisions you make in storage class selection create those budget traps. We're going to give you the playbook.
A roadmap, basically. We're going to unpack the four core pillars of GCS pricing, expose those critical financial trade-offs, which I think is the root of the problem for a lot of people.
It really is.
And then detail the modern optimization strategies like AutoClass and advanced object lifecycle management that you need to stop those hidden fees from eroding your bottom line. We're aiming for mastery here. Okay, let's unpack this. So we have to start with the foundational math. Before we can even talk about optimization, we have to understand the structure.
You have to.
Our sources laid out very clearly that the total cost of GCS is the sum of four primary pillars. If you miss one, you fail at budgeting. It's data storage, network usage, operations, and then those lurking supplemental fees.
That's the critical synthesis. The common mistake, especially from a management perspective, is to focus entirely on Pillar A data storage
Of course.
because it's the easiest metric to track,
Right.
like the raw gigabytes per month. But so often, the other three pillars can account for the vast majority of your unnecessary spend.
Okay, so let's start with that fundamental component then, just to get the terminology down.
Let's do it.
Pillar A data storage at rest.
This is the volume component, pure and simple.
So the costs are calculated based on the volume of data stored, measured in gigabytes per month. But, and this is the first crucial point, the final price you pay per gigabyte is entirely dictated by the storage class you assign to the object.
Yes, and this is where we get into the whole concept of the data temperature scale.
Right. Hot, cold.
Exactly. And you should think of this spectrum not just in technical terms, but in like commitment terms. We're scaling from boiling hot data that you need instantly
Mhm.
all the way down to legally frozen data where you commit upfront to almost never touching it.
And definitely not deleting it early.
Definitely not. The lower the temperature, the lower your storage cost, but the higher the commitment and the penalties for breaking that commitment.
So let's start at the hot end. The most flexible and also the most expensive tier is standard storage.
Mhm.
This is for your frequently accessed data, anything where you can't tolerate a delay. We're talking website assets, active data sets for analysis, streaming media.
Real-time transaction data, that kind of thing.
Exactly. And the core feature here, which we're going to come back to again and again, is that standard storage has no minimum storage duration.
That flexibility is what you are paying that premium for. You can put data in and take it out 5 minutes later with zero penalty.
Okay, so moving cooler, we get to nearline storage.
Right, so Nearline is designed for data you expect to access less than once every 30 days. Think of this as your monthly reporting archives or older application logs that you might still need for troubleshooting.
So it's not totally cold, but you're not hitting it every day.
Not at all. And the critical requirement here is that the service mandates a minimum retention of 30 days. That is your first financial commitment. You're telling Google, I guarantee this data will stay here for at least a month.
And stepping even further into the cold zone, we hit cold line storage.
Cold line. This is for data you access less than once every 90 days. So this is your classic disaster recovery data, maybe quarterly business intelligence snapshots, that sort of thing.
And the commitment here gets longer, right?
It does. It requires a minimum retention of 90 days, 3 months.
And finally, at the far, far end of the spectrum, we have archive storage.
Your deepest, coldest data. This is stuff held strictly for long-term legal, regulatory, or, historical reasons. We're talking about data you access less than once a year. Maybe.
And the commitment here is the longest and most rigid.
It is. A minimum retention of 365 days. This is basically the cloud equivalent of a secured offsite vault. You put it there and you plan to forget about it for a year.
I want to circle back on something you said about the why behind these tiers. Why exactly does Google care about these retention periods? Is it just like punitive?
That's a great question. And it's not entirely punitive, no. From an engineering perspective, there's a huge difference in how they provision and manage the infrastructure for these tiers.
Okay.
Standard storage is on high speed, instantly accessible disks, constantly online, aggressively replicated. When you move to archive, Google Cloud knows it can use slower, cheaper, and denser media. They can optimize the physical placement of that data, maybe even migrating it to infrastructure that isn't instantly available. They offer that massive discount because they're banking on the fact that the data will sit still for 365 days.
So the retention period is their mechanism for financial certainty on their hardware investment.
That's it exactly. It's a contractual guarantee. It ensures their low-cost infrastructure remains economically viable for them.
That makes perfect sense. They're asking you, the user, to bear the risk of early removal if your usage pattern changes.
Precisely. And that risk links directly to the financial traps we're going to get into later, specifically that early deletion fee.
Okay, on to pillar B, network usage or data movement.
Right, the second pillar. And this is often the first major source of surprise bills for new users.
The starting rule here seems beautifully simple, though. Data coming into GCS, what we call ingress, is always free.
Always. Google always wants your data. The charges and all the complexity only apply when data leaves GCS. That's egress.
And this egress has a sort of hierarchy of expense.
It does. Understanding this is key to efficient regional planning.
At the cheapest end, often free or nearly free, is intra-region egress.
The golden zone.
Right. So this is data transfer between your GCS bucket and another Google Cloud service, like a VM or BigQuery, that is all located within the exact same geographic region.
Because the data transfer stays entirely within Google's local data center network, it's cheap for them, so it's cheap for you.
Then we get to level 2, where charges become noticeable. Inter-region egress.
This is when you move data between two different regions. For example, if you have a bucket in Asia and you need to analyze that data with a service running in the US,
Okay.
that movement incurs a specific, often high charge because the data has to traverse long distances over Google's global private backbone.
And finally, the highest cost, level 3, is internet egress.
The big one. This is moving data from your GCS bucket out to a user on the general internet, someone downloading a file to their phone.
And that's almost always the most expensive category of data movement.
By far. And it's what you have to actively work to minimize, especially for applications serving a global audience.
So if I'm getting this right, the further the data has to travel and the more it involves external non-Google infrastructure, the higher the price.
That is precisely the case. You're paying for the mileage. And that's why regional planning, which we'll get to in Section 4, is not just about latency. It's a fundamental financial strategy.
Okay. Pillar C, operations, the hidden request costs.
This is the one that causes the most unexpected sticker shock. People budget for the volume in gigabytes and maybe the movement, but they completely miss the cost of simply talking to the storage system.
Right, the cost of the application making API calls to the bucket.
Yes. The core principle is that GCS charges you based on the sheer number of requests or calls made to the service, regardless of the data volume.
So if I download a 10 gig file, that's one operation.
One Class B operation. But if you ask for the list of contents in a bucket 10,000 times,
That's 10,000 Class A operations. I'm charged for the frequency.
you're charged for the frequency, not just the size. And these operations are split into two classes, and their cost difference is substantial.
First, we have Class A operations. These are the expensive ones.
Right, because they are resource intensive, they're defined as metadata intensive and write operations. The service has to do more work.
So what are some examples?
Concrete examples would be insert for putting a new object in, update, compose, copy, and the one that often brings down entire budgets, list.
Okay, wait. Why is list so expensive compared to a get? I mean, shouldn't just listing the objects be easier than downloading a whole terabyte of data?
That's a great question, and it gets to the core engineering reality of object storage. You might think of a GCS bucket like a file system folder, but it's not. It's a massive, globally distributed database.
Okay.
When you run a list operation, especially on a bucket with billions of objects, the system has to scan and retrieve metadata for potentially millions of objects and present that consistently.
So it's like a database query.
It is a database query at scale, and that requires more intense processing, more CPU, more locking, more internal overhead than just streaming a binary file from a disk, which is what a get does.
So the system is billing me for the complexity of ensuring that consistency.
Exactly. That's why Google puts list in the higher class A tier.
And then there's the cheaper alternative, Class B operations.
Yep. These are primarily your reading operations. They're less taxing. So get downloading the data and get metadata. They are billed at a significantly lower rate.
So quick recap, if your application is constantly asking what files have arrived by polling the bucket with that expensive list operation.
Those Class A costs stack up fast, and they can often dwarf your actual storage bill.
All right, and that brings us to the last pillar, Pillar D, supplemental fees.
The penalties. These exist strictly to enforce those contractual agreements we talked about with the storage classes, and they only apply to the cold tiers: nearline, cold line, and archive.
So if I use standard, I never see these.
Never.
The first one is the data retrieval fee. This one seems like the most surprising.
It is. It's a specific per gigabyte fee that's charged in addition to any network egress charge when you read or download data from any of those cold tiers.
So it's the cost of defrosting the data.
That's a perfect way to put it. It's the service charging you for the labor to make that object available quickly. Standard storage has no retrieval fee. When you move to a cold tier, you lower your monthly rate, but you introduce this immediate punitive cost every time you want to access that data.
So if I move 10 terabytes to archive to save $100 a month, but then have to pay 5 cents a gig to retrieve it, I've just introduced massive financial volatility into my budget.
You absolutely have. You've exchanged a fixed, predictable rate for a low rate combined with the risk of a massive variable fee.
And the second fee, the one that makes everyone wince, is the early dilution fee.
This is the hammer. This is what enforces those 30, 90, and 365-day minimums.
So how does it work?
If an object is deleted before its minimum period, you are immediately charged the remaining storage cost as if the object had stayed for the full duration. You broke the deal, so you pay the remainder of the contract. Google is just recovering the promised revenue stream that let them offer you that super low rate in the first place.
Okay, so that sets the stage. Now let's get into the application of these pillars. This is where the financial engineering gets really intense, right? When cheap storage isn't actually cheap.
This is it. This is about recognizing that every time you choose a storage class, you are making a calculated trade-off between the cheap fixed cost of storage and the volatile variable costs of access and deletion.
The first strategy, then, is about aligning the storage class with the data temperature. And the advice here is kind of non-intuitive. It says use standard storage for any data access more than once a month.
Even if its storage rate is numerically higher, yes. We really need to walk through the numbers slowly here because this is the clearest aha moment for cost management.
Okay, so here's where it gets really interesting. Let's dive deep into why paying more upfront is actually the smart financial strategy for some of this data.
All right, let's set the stage. We have a hypothetical scenario. 10 terabytes of data. And we're debating between standard and cold line. We use some hypothetical race.
Okay.
Let's say standard is 2 cents per gig per month. Cold line is much cheaper, say 0.7 cents per gig per month. And the cold line retrieval fee is 1 cent per gig.
Okay. First, the raw storage numbers. 10 terabytes is 10,240 gigabytes.
Right. So for the standard cost, 10,240 gigs times 2 cents. That's $204.80 per month.
$205. Okay.
Now for cold line, 10,240 gigs times that tiny rate, $0.007, comes out to just $71.68 per month.
Wow. Okay. So just on storage, cold line is dramatically cheaper. You're saving over $130 a month right there. I can see why managers are drawn to that number.
That is the lure. That's the bait. But now we introduce the risk. Because that data is in cold line, it incurs that retrieval fee of 1 cent per gigabyte.
So if an application or maybe an unforeseen audit requires a single full read of that 10 terabytes during the month?
Uh-huh.
we trigger the fee.
And the cost of that single retrieval is 10,240 gigabytes times that 1 cent, which equals $102.40.
And that's just the retrieval fee. That's not even the network cost to move it.
Not at all. That's just the cost to access the data.
Okay, so $100. That's a significant charge. Now, what happens if that data needs to be fully read twice in the month?
That's the moment of maximum financial exposure. Let's calculate the total cold line bill for that month.
All right.
You got your fixed storage cost of $71.68, and then your retrieval fees are $102.40 times 2, which is $204.80.
So the total cold line bill is $71.68 plus $204.80. That's $276.48.
That's it.
Wait. That's way more than the standard storage cost. We would have just paid a flat $204.80 for standard. We tried to save money and ended up spending an extra $70.
Precisely. The volatility of that retrieval fee just completely eliminates the perceived savings. The 0.007 per gig rate is financial bait if your access pattern is anything but religiously infrequent.
So the takeaway is that you have to view that low storage rate as a commitment, and the retrieval fee is the cost of breaking that commitment to dormancy if you don't trust your access patterns.
Standard storage is your safest hedge against that volatility.
Okay, now let's talk about the other trap, the early deletion nightmare scenario.
If the retrieval fee is the trap for accessing data too often, this is the penalty for not committing long enough. This is where that minimum financial commitment becomes a landmine for temporary data.
Let's look at the mechanics. We'll use archive storage as the example with its 365-day minimum.
Okay, imagine you upload a 100 gigabyte batch of data to archive. You needed it for something, but maybe the process failed or the data was just temporary, and you delete it after only 10 days.
Most people would expect to pay for just 10 days of that ultra-cheap archive rate, which is basically nothing.
Right. But the reality is you pay for those 10 days of storage, plus the early dilution fee for the remaining 355 days.
So the fee is calculated as the cost of storing the data for the rest of the minimum period.
Correct. You effectively pay for a full year of storage for a file that only existed for 10 days. The system doesn't care that you made a mistake. It just enforces the contract that allowed you to get that ultra-low rate.
This means the optimization advice has to be incredibly strict. Always use standard storage for any temporary files, scratch data, anything with an undefined lifespan.
The tiny savings on the gigabyte rate are completely irrelevant compared to the risk of triggering this massive deletion penalty. And this is perfectly illustrated by a data science use case in our sources.
Okay, let's do it. Exercise 1, intermediate data selection. So a data science team runs a nightly job, and it generates 500 gigabytes of intermediate data. This data is critical for the job, but it is explicitly designed to be deleted every single morning when the process is done.
Okay, so if they choose nearline storage, which is cheaper per gig, they immediately trigger that 30-day minimum retention rule.
They delete the 500 gigs after maybe 12 hours.
And the financial penalty is they incur the early deletion fee for the remaining 29+ days.
And since they run this job every night, every single morning, they trigger another 29-day fee for another 500 gigs.
Over the course of a month, they would be accumulating 30 overlapping early deletion fees. The cost would be astronomical. And if they chose archive, the penalty period jumps to 364 days daily.
So the only financially sound answer is standard storage.
The only one. Standard's higher rate doesn't matter because its key feature zero minimum retention means deleting that data after 12 hours costs $0 in penalties. For temporary data, Standard's flexibility makes it the cheapest solution available.
And just to be clear, what's the ideal use case for something like archive storage?
The ideal use case is data that must adhere to WARM principles. Write once, read many. This is immutable, regulatory mandated data, like for SEC or HIPAA requirements, where you are legally required to keep it for 5 or 7 years.
And you know with absolute certainty it will not be deleted before that compliance period is over.
It's fixed and forgotten. That's what the archive tier was built for.
Okay, it's pretty clear that manually assigning storage classes and trying to manage all this is just a recipe for error. One slip up, one temporary file in cold line, and the budget is blown.
Exactly. Which leads us to the absolute necessity of moving from manual labor to automated smart management.
This is your defense against human error.
And against the volatility of those fees. We're dealing with two main tools here. The new hands-off GCS auto class and the more traditional rule-based object lifecycle management, or OLM.
Let's start with the modern solution, GCS auto class. This seems like a really critical strategy.
It is. The moment you enable AutoClass on a bucket, it completely eliminates the need for you, the admin, to manage storage classes manually. That's a huge operational and financial benefit.
And how does it work?
Its functionality is built around observation. It automatically transitions objects between standard, nearline, cold line, and archive based on the observed access patterns over time.
So if an object just sits there untouched for 30 days.
AutoClass will autonomously move it to nearline for you, cutting your fixed storage cost. But then if that object is suddenly accessed frequently again, it quickly bumps it back up to standard to avoid those retrieval fees.
So the key advantage isn't just the hands-off approach, it's that AutoClass is smart enough to handle the financial trap.
It is. It eliminates management overhead and, crucially, it's designed to inherently avoid the early deletion fees that can plague manual rules.
How does it do that?
It manages the transitions based on access, and it manages the minimum retention periods internally. So it ensures that when an object is moved, it has already satisfied its financial commitment period. AutoClass basically automates our strategy one for you.
So if AutoClass is so smart and safe, why would anyone ever use the older rule-based method?
That's the perfect transition. AutoClass is fantastic for generic fluctuating data, but Object Lifecycle Management, OLM, is still vital when you have extremely predictable data, strict regulatory requirements, or you need automation based on something other than access.
It's the rule-based alternative.
It is. It allows you to define specific rules based on object age, creation date, versioning. It executes exactly as written, which means you still have to be incredibly careful about those minimum retention periods we stressed earlier.
So what can OLM do?
It uses two core types of rules. First, there are transition rules. These automate the downgrade of the storage class. So a common scenario is move objects from standard to cold line after 60 days of no access.
Okay,
to dictate the timing.
And the second type?
Deletion rules. And this is probably the most important continued use case for OLM. These automate cleanup based on criteria that AutoClass doesn't handle, like versioning.
Okay, so give me an example.
Delete version objects after 5 newer versions exist, or delete all logs older than 365 days, regardless of when they were last accessed. OLM ensures mandatory cleanup.
So when do you absolutely have to choose OLM over the easier AutoClass?
3 critical scenarios. 1, strict compliance. If your industry requires data to move to archive on a specific date, you need the explicit rule setting of OLM.
Because AutoClass is based on observed access, not a mandated aid.
Exactly. 2, version management. If you need to clean up previous versions of an object, OLM is required. And 3, mandatory deletion. If a file absolutely must be deleted on a certain date for, say, privacy law reasons, OLM provides that deterministic rule.
So OLM is the scalpel for specific requirements, and AutoClass is the broad safety net for general use.
That's a perfect way to put it.
Okay, let's circle back to Pillar C, operations costs and the expense of those Class A operations, specifically that costly list operation.
Right. If you manage high-volume data streams, the cost here can just balloon almost invisibly.
And the problem comes from a legacy application pattern called polling.
It's so common. This is when an application continuously asks GCS, is there a new file yet? Is there a new file yet? And it checks by using that expensive list operation every few seconds.
I can see this spiraling. One microservice polls every 10 seconds. That's 6 times a minute, 360 times an hour, over 8,000 times a day.
And if you have 50 microservices doing that, those Class A costs are generating 0 business value. They're just checking an empty mailbox. We've seen scenarios where this mistake results in an operations bill that is 10 times higher than the storage bill.
A $50,000 bill just for listing requests? Wow.
Just waiting for an event that might not even occur.
So the solution is elegant. It's strategy 4. Switching from polling to a cost-efficient, event-driven architecture using pub sub notifications for GCS.
Exactly. Instead of the application asking GCS repeatedly, GCS becomes the initiator. When a new object is created or deleted in the bucket, GCS immediately triggers a notification via the pub sub messaging service.
And your application just subscribes to that message queue. It only wakes up when there's actual work to do.
It's the difference between standing at the post office demanding to know if your package has arrived versus just getting a text when it lands. You only engage in the costly activity when the event is confirmed. It's a crucial strategy for eliminating those wasteful Class A list operations.
Okay, our final major area of optimization focuses on that second most painful cost center, egress, data movement.
Right. We established that internet egress is the highest cost, and inter-region egress is also expensive. The goal is to maximize free or discounted movement.
Which brings us to strategy 3, network efficiency. And the primary way to do this is through smart geographic planning.
Rigorous geographic planning. Every time a bit leaves its region, someone pays, and usually that someone is you.
The core concept here is co-location. It's simple, but so often overlooked. It just means placing the GCS bucket in the exact same region as the consuming service.
So if your compute engine VMs or your Kubernetes cluster is running in US Central 1, your GCS bucket must also reside in US Central 1. The simplicity is its power.
And why is this so crucial financially?
Because co-location transforms expensive inter-region egress charges into free or heavily discounted intra-region egress. You shift the data movement from a charged long-distance service to a free local data center service.
Let's apply this. Exercise 2, regional planning. So we have a high-traffic e-commerce company. They run their web servers in US East 1.
Okay.
But maybe years ago, they deployed their static asset bucket, all the product images in CSS and US West 1 because the storage rate was a tiny bit lower back then.
I've seen this happen so many times.
So every user request for a web page asset means the server in the east reaches across the entire country to the west to fetch the image.
Correct. The data travels from west to east, crossing a regional boundary and incurring an inter-region egress fee on every single asset loaded by that server.
And on a high-traffic site, that network bill for this simple oversight could be immense. Tens of thousands of dollars a month just for 3,000 miles of unnecessary travel.
Absolutely.
And the cost reduction strategy is immediate. Move the GCS bucket to US East 1, co-locate it with the web server.
And you eliminate that inter-region egress fee instantly. It provides massive daily savings. Regional planning is a financial necessity.
Okay, so co-location handles internal traffic, but we still have to tackle the highest cost traffic, internet egress, moving data to users across the globe.
And this is where cloud content delivery networks, or CDNs, are absolutely essential.
So Cloud CDN is specifically designed to shield us from the cost of serving public-facing assets directly from our GCS bucket.
The mechanism is a masterpiece of distributed architecture. The CDN caches your content at edge location servers globally placed close to your end users.
So when a user requests content, they download it from the nearest cache, which is faster and, crucially, cheaper.
Right. By serving content from the cache, you drastically reduce the amount of high-cost internet egress that's billed from the GCS bucket. You still pay for CDN egress, but the rate is typically much lower.
And the volume of traffic hitting the high-cost GCS origin is dramatically reduced.
That's the other key.
Yeah.
Let's use the savings calculation from our sources to really quantify this.
Okay, exercise 3. CDN impact calculation. We're serving 1,000 gigabytes, 1 terabyte of video per month.
Right, and let's say the baseline internet egress without a CDN is 12 cents per gig. The CDN egress cost is 8 cents per gig, and we'll assume a strong 90% cache hit rate.
Okay, first the baseline. Cost without a CDN, 1,000 gigs times 12 cents. That's $120 per month. That's our starting line.
Now let's introduce the CDN. Total traffic is still 1,000 gigs. 90% of that, so 900 gigs, is served from the cache at the lower CDN rate of 8 cents.
And the other 10%, 100 gigs, is a cache miss. So that has to be pulled from the GCS origin bucket at the higher GCS internet egress rate of 12 cents.
Let's run the math. The CDN cost is 900 gigs times 8 cents, which is $72.
Okay.
The GCS origin cost for the cache miss is 100 gigs times 12 cents, which is $12.
So the total cost with the CDN is 72 plus 12. That's $84.
$84.
That's a huge return, a savings of $36 a month on just that 1 terabyte. The CDN saved us money by reducing the expensive traffic volume from GCS and by providing a cheaper rate for most of the traffic it served.
Absolutely. When you scale this architecture to petabytes of high-traffic content, that difference translates into hundreds of thousands of dollars in savings annually. For any public-facing asset delivery, the CDN is mandatory for cost management.
This has been a really comprehensive deep dive. We moved way beyond just the low per gigabyte rate, and we've analyzed the 4 pillars that determine your total GCS spend.
The volume, the movement, the frequency of operations, and those critical penalty fees.
So the synthesis is clear. GCS is absolutely not a set-and-forget service.
Not at all. It requires active management, even if that management is automated. To be truly cost-effective, there are 4 actions that are mandatory. This is your post-dive checklist.
Okay, action 1. You have to monitor access patterns rigorously. Use tools like cloud monitoring. If you don't know how often your data is being read, you're playing Russian roulette with retrieval fees.
Action 2. Automate your storage transitions. Use the safety net of AutoClass for general data, or the precise control of OLM for compliance and mandatory cleanup. This removes human error.
Action 3, minimize data movement. Use colocation for all internal services to leverage free intra-region egress and deploy Cloud CDN immediately for all public-facing assets to cut down on that expensive internet egress.
And action 4, eliminate expensive polling. You must transition to event-driven architectures using things like pub/sub notifications for your operational workflows. It's the only reliable way to stop generating massive, unnecessary Class A request billing.
So what does this all mean for your future infrastructure planning?
It means you now have the roadmap to controlling your cloud spend. You understand that selecting the storage class with the lowest monthly rate is often a deliberate financial booby trap if you haven't accounted for access frequency and those penalties. You have to budget for risk, not just rate.
And here is a final provocative thought for you to chew on as you review your own architecture. The most efficient storage class is standard if you don't fully understand your access pattern. Consider the immediate and substantial cost of a single full retrieval from archive storage. That retrieval fee is applied to every single gigabyte you pull out. That single unforeseen cost could easily outweigh 12 months of storage savings if a single compliance audit forces you to retrieve that data just one day after the minimum retention period is met.
That potential for sudden, massive financial volatility is the real hidden risk in aggressively managing cold data. You're trading fixed, predictable spending for a cheap rate coupled with high, unpredictable risk.
Use that knowledge wisely to build better, cheaper, and more stable cloud systems. Until the next deep dive, stay informed and stay optimized.